we're working with proportions, again, only we're going to have problems that have similar figures and scales and things like that. So it's more of applying the proportions. So doing the problems we did yesterday, but applying the things. And we're going to start out with a lot of information. I mean a lot of information. Okay, first thing, similar figures. Have the same shape, but not necessarily the same size. Okay, this is something you're going to, that if you take geometry next year, you're really going to discuss a lot with similar figures. Okay, all squares are similar figures because all squares have the same shape. They do not all have the same size. They all have the same shape. That's what it means to be similar. They have the same shape, but not necessarily the same size. That's what similar figures are. So if you think of all squares, they're all similar. All circles are similar. They may not be the same size, but they all have the same shape. Okay. A scale drawing, some of you may have already worked with these. Drawing that is similar to an actual object or place, but not the same size. Think about architectural drawings. Those are scale drawings. They're not the actual size of the buildings. It's not playing with the fingerboard. Yeah, you don't draw architectural plans the same size as the house you're going to do. That'd be an awfully big piece of paper to be drawing them on. You draw a scale drawing. The scale is the ratio of any length of the drawing to the actual length. So if you ever look at a map or you look at a scale drawing, you'll say what's the scale at the bottom. 1 inch equals so many feet, or 1 inch equals so many miles, or something like that. Okay.
You might find something like this at the bottom of a map.
Or any scale drawing as far as that goes, not just maps and stuff, but any kind of scale. If you build plastic models, it gets the scale on there, 1/24 scale. That means 1 inch on the model equals 24 inches in real life. Okay. And I have 2 on this one. I don't know why there's 2 on that one. A scale model is a 3-dimensional model that is similar to a 3-dimensional object. Like I said, if you see plastic models and stuff, or you see the toy cars are scale models. Some more accurate than others, as far as their scales go, but those are scale models. Often an architect will build, particularly if it's a large object they're making, they will build a scale model, a 3-dimensional model of it, not the full size, but a scale one, in order to be able to visualize what it's going to look like better. Yeah, I've done that before when designing things, building stuff. Okay, I'm going to build a smaller version out of cardboard rather than the large version out of wood or something like that, so I can get an idea what it looks like, what it's going to look like. Okay. Now, a couple of things you're going to need to remember for today, and these are geometric formulas and properties. Okay. I have triangle ABC, and we'll be working with this in later things. This is how you write out triangle ABC. So if I have a triangle and the 3 corners are ABC, this is triangle ABC. Triangle DEF. This little squiggle in between, technically it's called a tilde. If you've ever seen it, it's on top of a letter, it's called a tilde. The little squiggle in between means that those two are similar. Means that those 2 triangles have the same shape. Not necessarily the same size, but the same shape. Okay. It's a geometric term. Okay. You want to say that 2 things are similar, you label one, label the other, and you put the little squiggle in between. That means they're similar. That means they have the same shape. Okay. And then here I have, this is the symbol for angle, angle A, angle F. If you have an equal sign with a little squiggle on it, that doesn't mean they're similar. That means they are congruent. That means they're exactly the same size. Same shape, same size, they're exactly the same. In geometry, we don't call objects. Objects are congruent, sizes are equal. It's a goofy thing. But if we're talking about the object, and the angle A is an object, then we say the angle is congruent. If we're talking about the size of the angle, how much we measure it, like 25 degrees, we might say that they're equal. But when we talk about the objects themselves, we say that they're congruent. Okay. Questions so far? I think it's a lot of information at the beginning. Now, here's where we're going to actually use them. In the diagram, triangle ABC is similar to triangle DEF. Triangle ABC is similar to triangle DEF. Okay? They have the same shape. They do not have the same size, but they have the same shape. Here's the thing about similar figures. Corresponding sides are proportional, so we can write a proportion using corresponding sides. That's what we're going to do today. We have similar shapes. We can find something we want. Now the question asks us, what is DE? How long is DE? We're given some of the lengths. We're not given DE. This is the one we're looking for. Okay, so I'm going to label that X. Because we don't know it, what do we call it? We call it X or some other variable. I'm going to use X because I like to use X. Okay. So that's what we're looking for. Now what we need to do is match that corresponding side to that side to the corresponding one on the other one. In other words, if I were to take these two and lay them on top of each other, which side would match up with it? Now, there's two ways to do this. You can either look at it visually and say, hey, I've got this line here, which means it's going to line up with this line here. So those two are corresponding sides. Do you see how they line up with each other when you're looking at the diagram? The other way to do it is I have AB and DF. Where do the letters line up in the name? If the letters line up in the name, then those are corresponding sides. So AB and DF. So what I do is I write a ratio of those two sides. Okay? And I'm going to use this triangle first and that triangle second. So I put 10 over X equals. Now I have to look at the other sides in the triangle and find corresponding sides in the two triangles that I know how long they are. Find two sides that match up that I know how long they are. Okay, so any ones where I look at it, well, I'm given this one here is the only one that's with the measurement I'm not already using. So I have this length here. Which side does it match up with on the other one? Yeah, EF, which is 12. So I have this side to that side. So now I can set up a ratio with these two as well. Now, this triangle was on the top in the first one. This one was on the bottom. So that means the corresponding sides, let's do that again. I have 16 over 12. 10 and 16 came from the same triangle. X and 12 came from the same triangle. Okay, does that make sense? And now this is a proportion. This is what we were doing yesterday. These are easy to solve from here. Cross multiply. That's what you do. Cross multiply. X times 16. 16x equals 10 times 12, which is 120. Divide both sides by 16. Excuse me. And I get x equals, what do you get? 7.5. So that means that this is 7.5. Okay? The hardest part is figuring out and setting up the proportions. Once you get the proportion, it's not that difficult to do. But if you look at the diagram and look at the pictures, that will tell you, ooh, this one lines up with that one. This one lines up with that one. Okay? So So let's do this one here. Same idea. What side am I looking for? AC. So I find AC. I'm looking for this, and I'm going to call that X, because that's what I'm looking for. So I have one side AC in the first triangle. Which side in this second triangle does that line up with? Lines up with DF, this one here. So that means I have X and 18. Those are my two sides. I have X over 18 equals. And now I want to do the same thing with two other sides in the triangle. So I can't use these two again. I've got to use two other corresponding sides. Well, in this triangle, this is the only length I have. Here's that one, EF. Which one corresponds with EF in the first triangle? Which one lines up with it? Yeah, the length at 16, which is BC. So that means the two sides I'm going to work with here are 16 and 12. Okay. Which one's going to go on top, the 16 or the 12? The 16, because the X is the one on top here, so the 16, because it's from the same triangle, needs to go on top here. So I get 16 over 12. Okay. And once you get that, cross multiply. X times 12, 12x equals 16 times 18. What do you get for 16 times 18? 288. Divide both sides by 12, and you get x equals, is it 20? No, 24? 24. When you are doing this with your classwork, I cannot recommend strongly enough you do like I did here. Ooh, this one to this one, this one to this one. Draw little lines on there. Indicate which ones are matching with which on your drawings when you're doing your classwork today. Bless you. Okay, now we get to applying similarity. The first one is actually an extremely common practice. It's an ancient one. It's been used forever. Using shadows to find out how tall something is. That still can be done today. It's not nearly as common because we have other methods professionally for finding stuff. But figuring out how tall something is using a shadow, it's not an uncommon thing. Not an uncommon thing at all. What I have is I have two similar triangles here. Okay. Now it's hard to read on mine and it's hard to read on your paper, but because the X is inside, but that is X. That's what we're looking for. Okay. So I have two triangles. I have the small triangle and the large triangle. And I want to do the same thing. I want to set up a proportion for the two triangles. And I do the corresponding sides. Now, I have this length here, 3 feet, corresponds with this length there, 15 feet. 3 over 15. And then I have two lengths in the other one. I have the young lady's height and the height of the building. Which one's going to go on top, the 5 or the X? The 5, because which one went on top the first time? The 3 that goes with the 5 from that triangle. The same triangle goes on top. The little one on top, big one on the bottom. So I have 5 over X. And then you cross multiply. 3 times X equals 5 times 15. Divide by 3. X equals 25. So it's 25 feet tall. questions so far? Good application of using similar triangles. Now this next one is very much like what you were doing on your in the word problems yesterday. A couple of the word problems had scale in it. Same thing. Only this one we've got a picture instead. So first thing we want to do is we want to figure out our scale. What are we comparing? There's our scale right there. That's usually what you'll find on a map somewhere. Is you'll find the scale written somewhere in a corner of the map or at the bottom or something like that. So my scale is 1 inch to 110 miles. So I have inches to miles. Remember the units. We were talking about the units the other day. Keep your units straight. So I have inches over miles. So the scale says I have 1 inch for every 110 miles. And that equals, well, I want to find the distance from Jacksonville to Orlando. Okay. Now the ruler is kind of hard to read on your diagram. It's not really easy to read up here either. But if you read it carefully, it ends up being 1 1/4 inches or 1.25 inches is the distance with a ruler between the two cities. Okay. So that is measured in inches. So I have inches over miles. So it's 1.25 over X miles. And this one's nice. Because when I go to solve this, I go, ooh, 1 times X. What's 1 times X? X equals 110 times 1.25. What's 110 times 1.25? Somebody do it on your calculator. What do you get? What? 137.5. Anybody else? 137.5. Confirm. Okay. 137.5 miles. So it's 137.5 miles between Jacksonville and Orlando. If you're driving a perfectly straight line, we're not going to be driving a perfectly straight line. That just doesn't do it. Questions on this one? Okay, uno más. Okay, we are going to connect the zip line from the top of the E building, right up there, down to the flagpole. We got a problem with that. That wouldn't really work in real life, would it? Because if you stand out here on the balcony, you cannot see where the flagpole is. Adding an extra 10 feet to get a little taller probably isn't going to work. You got a few buildings in between that you're probably going to run into before you hit the flagpole. So in real life, that wouldn't work. Unless we had a tower at the flagpole, yeah, I don't think that would really work. But that's okay. We can dream, can't we? Then we have a zip line. So instead of having to walk down the flagpole, we just got a line of kids wanting to go down the zip line instead. Wouldn't you rather do that? Yeah. Yeah, I imagine a bunch of you would. Not me. No. Okay. So we have that idea. Now, this is a scale drawing. This is a scale picture. What's our scale? Our scale is right here. What are the things we are comparing in our scale? What are the measurements we're talking about? Okay, what are the units that we're comparing in our scale? Inches to feet. So we have inches to feet. And our scale has 1 inch for every 21 feet. Okay. Now, there are measurements, and once again, it's a little difficult to read on yours. A little easier to read on this one because it's in color. It's in black and white. It's a little easier to read. What's our measurement on the picture? This is 25 what? Inches. So I have inches over feet, so I get 25 over X, which is our actual distance we want. And then what do? We cross multiply. This is also, once again, a very easy one. 1 times x is x. And then 21 times 25. 525. It's 525 feet of cable. Easy peasy. Okay. So the problems are easy problems. The difficult one today is setting up the problems to begin with. Okay. Any questions? Awesome sauce.